So you got questions about grading, you can ask me during office hours, obviously. And I do post a solution, so if you look at the solution and find out you're completely right, or my solution's wrong and you're right, you may, of course, talk to me about that. So this is Psalm 37, and this is verse 6. It says, well, verse 5. It says, "Commit your way to the Lord. Trust also in him, and he will do it. He will bring forth your righteousness as the light, and your judgment as the noonday. Rest in the Lord and wait patiently for him. Do not fret because of him who prospers in his way, because of the man who carries out wicked schemes. Cease from anger, forsake wrath. Do not fret. It only leads to evil doing." That's Psalm 37, verses 5 through 8. So I'll begin with a word of prayer. Dearly Father, we thank you again for your many blessings to us. Help us to glorify what we do this day and just understand a little bit more about inverse matrices, Lord. In your name I pray, Lord Jesus. Amen. Do you guys have any questions before I get into it? Here is the attendance sheet. If you can add a day to that, that'd be awesome. All right, let's see here. So last time I showed you guys like the, the basic theory of inverse matrices, and we learned a few different things that you want to kind of remember in this course because they'll help you solve problems, and it's especially important to remember equivalence of things that is not entirely obvious, right? Like some of the things we did last time, we kind of had to work hard to get these things to be true, right? So it's probably worth our time here to just state, theorem for a square matrix, n by n square matrix with real entries, the following are equivalent. All right, so number one, A inverse exists. Number two, there exists B in Rn by n such that BA is equal to the identity matrix. Number three, there exists B in Rn by n such that AB equals to the identity matrix. Number four, A is the product of elementary matrices. Let's see here, number five. Can you guys add one? What am I missing? What else did we prove last time? And when I say we, I mean me. I'm trying to include you in it, though. You're like, don't include me in it. I'd rather not be included in the proof, right? It's enough for us to know these things, yeah? How about this? AX equals to 0 if and only if what? X equal to 0. That's right. There's another one. How about if I was to say RREF of A, what would you tell me it's equal to? I. Very good. Is there anything else? How about this? AX equals to B has a unique solution for any choice of inhomogeneous term B. Anything else? I think on the surface of it, these all look like they're pretty different conditions, right? There's another 8. If we look at the set, column 1 of A, column 2 of A, column, n of A, right, is what? What property does the set of column vectors have? Yep. Linearly independent, right. Linearly independent. I think that should hold us for now, but that's our current list of equivalent conditions on the invertibility of a matrix. These are all the different ways we can look at it. The textbook I think it's by Anton, he's got this running theorem as he goes on in linear algebra. By the end of the course, he's got this list of like 20 equivalent conditions to the invertibility of a matrix. All right. So let's look at an example. Let's suppose A is equal to 3, 4, minus 2, 1, and then we'll do 0, 0, make my life not too horrible. I don't know, 3. Let's find the inverse matrix to this. All right, we should do one of these. So how do we calculate the inverse matrix? What's our method, our calculation of method? What we do is we augment the matrix A, right? We look at A concatenated with the identity matrix. So that is 3, 4, 0, minus 2, 1, 0, 0, 0, 3. And then we've got ourselves a 1, 0, 0, 0, 1, 0, 0, 0, 1, like so. All right. Now you guys know row reduction, right? So what's going to happen eventually is we're going to get down to 1, 0, 0, 0, 1, 0, 0, 0, 1. And then over here what there's going to be is, let me think about it for a second. I think it's going to work out to 1 11th, minus 4 11ths, 2 11ths, 3 11ths, and 1/3. But you know what? Let's see if I'm right. That's my prediction after some row reductions. Okay, so let's see if we can do that. So what would you guys say we should start with? Maybe we can get rid of that too, right? So to do that, how about this? We do row 2 plus 2/3 row 1, right? If I do that, that should clear the 2 out. Do you guys see it? All right, so that would leave me with a 3, a 0, a 0. 4 0 stays up there. So which I'm not modifying rows 3 or row 1. So I might as well just write those down, and I'll put the other one in different color to emphasize that's where I'm changing things. All right, so what is 2/3 times 4? 2/3 times 4 is 8/3. What's 8/3 plus 1? 11/3. Interesting. There's an 11 on the scene now. How about, oh, the zeros? Well, that's nice. So that just stays 0. And let's see here, 2/3 are 1. So that puts a 2/3 here, I think. Is that right? And, oh, the others are easy. All right. Yep.
Should the middle zero be 1?
It should. Thank you. That is a very, very helpful comment. I appreciate it. Watch out. It's very easy to make a mistake, right? The good news is, after we're done with everything, we can check our answer, right? How do you check if the inverse is right or not? You multiply it, right? So we'll do that eventually. Now what's next? Let's see here. To get rid of that 4 with this, I could do what? I could do, Mom, I have to think about this. Goodness gracious. All right, you know what? I'm thinking too hard. I'm going to get rid of that 11/3. Let's multiply this guy by 3/11. Yeah. I don't want to think. I'm just going to multiply by 3/11. So that gives us a 3, 4, 0, 1, 0, 0. And then 0, 1, 0. Oh, I guess I do have to think. 2/11 apparently. Right? And 3/11. I regret my font choice. 0, 0, 0, and 0, 0, 3, 0, 0, 1. All right. That feels better. Now let's clear out that 4. Clear out the 4. How do we go? Row 1 minus 4 row 2. Right? So we're going to keep the 0, 1, 0, 2/11, 3/11, 0, and then keep the bottom row 0, 0, 3, 0, 0, 1. All right? The top row, how's it go? We got ourselves a 3. We just cleared that 4 out, and that's still 0. And then I got what? 1 minus 8/11, which is what? What's 11/11 minus 8/11? It's 3/11. Yeah, 3/11 there. And then, let's see here. What is 4 times 3 is 12. So minus 12/11, is it? And the 0 is still 0, I think. Right? And then I think that's enough to get from this down to here. What do? We do like 1/3 row 1 and 1/3 row 3. And that will get you to this. Which by magic I just wrote down at the start. How did I do that? That's because I know what we're going to talk about next week. Okay? So, yeah. That is not always possible. Like, generally speaking, you just have to do it. All right? The reason that was possible here is because this matrix has a certain pattern. It has what's called a block decomposition. So there's like a simple theorem. Anytime your matrix is block diagonal, the inverse of a block diagonal matrix is formed by just inverting each block and just putting them in the same order. But I know how to invert a 2x2 matrix, right? How do we do that? I mean, I'll at least explain this much to you guys. Like, what's 3, 4 minus 2/11 inverse? 2, 1 rather, inverse. Remember our formula? We do 1 over AD minus BC, flip the D in the A, and put minuses on the off diagonal if the matrix we're inverting is ABCD. And so what is that? 1 over 11. I flip the diagonals. Minuses on the off diagonals. And so there you have it. That's how I knew to put that block there. And then the inverse of the 1x1 matrix, what's that? How do you invert a 1x1 matrix? What's the inverse of the 1x1 matrix? 3. It's just 1/3. Okay. So there's like a theorem we'll talk about next time, eventually. I guess I'm talking about it now for the sake of making this example make more sense, but this is like something that's true. If you have a matrix which looks like this is A1, and this is A2, and this is the pattern of it, it turns out that the inverse of this is nothing more than the inverse like that. So, which means that if you have a block diagonal decomposition of your matrix, you can kind of divide and conquer. All right? Let's continue example 1 a little bit more. So like example 3, suppose I'm solving 3x plus 4y equals to 7 and minus 2x plus y equals to 8 and 3z equals to 9. Now, admittedly, that's not a very hard problem to solve, but I'd like to point out to you that this system we can solve with matrix multiplication. See, because this is the same as 3, 4, 0, minus 2, 1, 0, 0, 0, 3 times the vector x, y, z equal to the inhomogeneous term 7, 8, 9. Right? And this is the A, which we've just inverted. So what we're looking at here is AV equals to B. Right? AV equals to B, which we can symbolically solve to say that V is equal to A inverse times B. But A inverse times B here is literally 1/11 minus 4/11, 2/11, 3, I guess I could look there, 3/11, zeros, and finally a third down here, and I got to multiply that by my B, which in this case I just made it 7, 8, 9. So what's my answer? My answer is, what's 7 minus 28? So I think minus 21 over 11, then you got 14 plus 24, which I think is 38 over 11. And then you got yourself 9 divided by 3, which is 3. So there you go. That's the answer to that system of equations. Right? So we can solve, if we know the inverse to the coefficient matrix, we can solve the system by multiplication by the inverse. Right? This is an especially nice method if you're trying to solve, like, you know, all possible problems. Right? If I replace 7, 8, 9 with like ABC, this is a pretty nice method in that kind of problem, right? If you know the inverse matrix, then this is a pretty nice way to solve it. But what's the rub? Like in terms of efficiency of calculation. If you're just given a specific system of equations, right? And you're asked to solve it, is finding the inverse matrix the way to go? Like, is it faster than just doing Gaussian elimination on the augmented coefficient? It is not faster. But it's kind of in some sense equivalent, right? It's not so different either, though, is it? Because basically to calculate the inverse matrix, right, you have to do the row reduction to reduce the matrix to the identity. That's exactly the same thing that you need to do to solve the system. Okay, that's not entirely true, because you could actually stop short, right? Once you get the system to a reduced row echelon, just a reduced echelon form, not row reduced, you could back substitute the system, and that might be like way faster in terms of particular systems. And then furthermore, if you're dealing with like systems with lots and lots of variables, if you have an if you have a coefficient matrix which has got like big chunks of 0 in it, then that can make particular strategies that respect these zeros go way, way faster. So a matrix which has lots and lots of zeros is called sparse. All right. Okay, so anyway, let's see here. What else can I tell you? Oh, let's check it. Does this actually work? I think so. Let's check our answer. We can do that as well. What's our matrix? 3, 4, 0, minus 2, 1, 0, 0, 0, 3. And if this is the genuine inverse, when we multiply, we ought to get back what? So, multiply the matrices. So we've got what? We've got this times that gives me 3 11ths plus 8 11ths, also known as 11 11ths, more popularly known as 1. The second column, we get minus 12 11ths plus 12 11ths, also known as 0. And then we get 0. And then when we multiply this times that, I get minus 2 11ths plus 2 11ths, also known as 0. When I multiply this times that, I get minus and minuses plus 8 11ths plus 3 11ths, 11 11ths, 1. Again, 0. And then let's see here. In the last one, 0, 0, and finally the 3 times 1/3 gives me 1. So you can easily see that, in fact, yes, hooray, it is in fact the inverse. And thankfully last time we proved we only need to check that, right? If you check that A times A inverse, your alleged A inverse, gives the identity, you can be assured that A inverse times A is also going to be equal to the identity, right? So that proves that, in fact, we did calculate the inverse correctly, which is good news because that means that this is the genuine solution to that system. Now, of course, I think you guys could solve this system pretty fast anyway, right? At least I could. What would I do? I would just solve the last one, and then I have 2 equations, 2 unknowns, and however you see best fit to do that one, right? Any questions? We all good? All right. So another natural question to ask here is, how does transposition and inversion work together, or do they work together? What's the story there, right? And excuse me. So we should look at that a bit. And I should also give you kind of I should probably work out a symbolic problem, which is a little bit kind of sort of like one of the homeworks I've assigned you, just so you have a better kind of sense of how to work that homework problem. So let me do that before I forget. Yeah. All right, so here we go. Example 4. Let us suppose we have a 4x4 matrix and non-zero vectors v1, v2, v3, v4, all right, such that, here's the deal. We have AV1, if V1 plus V2 times A is equal to E1. We also have that A times V1 minus V2 is equal to E2. We have AV3 is equal to 3V3, not V3, my bad, E3. And we have AV4 is equal to, let's say, 4E4. Okay, so this is all given to us. And then the question here is to find the inverse matrix in terms of the given vectors. Now, what makes this problem a little bit tricky is that you can't just do the thing we did for example 1, right? Because you don't know A. You don't even know what precisely these vectors v1 and v2 and v3 and v4 are, right? All you know is that they are solutions to particular equations. Now this E1, E2, E3, E4, let us understand what these mean, right? This is 1, 0, 0, 0. This is the 0, 1, 0, 0. You know, the standard basis, right? So let me remind you guys, to solve the equation AA inverse equal to the identity, let me use a different letter than V this time. That's really like looking for vectors W1, W2, W3, W4 equal to, in this case, E1, E2, E3, E4, right? We're trying to solve that equation to find the inverse. But keep in mind, that's actually solving 4 separate systems of 4 equations and 4 unknowns. Those 4 equations we're trying to solve are AW1 equal to E1, AW2 equals to E2, AW3 equals to E3, and AW4 equals to E4. Like, we need to solve these 4 equations in order to find the inverse. 2 of these are pretty easy to solve, right? Like, do you see how to solve the last 2? How would you go about it? So I would just say, okay, well, hey, I'm given this, right? So if I divide by 3, a times 1/3 V3 is equal to E3. So, hooray! We got this, right? That would give me a nice solution for this one, right? So you can see, aha, we can just let W3 equal to 1/3 V3. Yeah? And if you see that, you probably can see that what to do with the 4th one, right? For the 4th one, notice that we can divide by 4, and we get a times 1/4 V4 is equal to E4. So looking at that, that suggests to me that we have the solution W4 is equal to 1/4 V4, right? So what do I do? What do I do with the other 2? Oh, I guess there's nothing to do, is there? Right? They're already what we're looking for, aren't they? Like, V1 plus V2 is E1, V1 minus V2 is E2, right? So I can already identify, after I have a moment's thought, right? W1 is V1 plus V2, that'll work. And W2 apparently is V1 minus V2. All right. So what's my inverse? My inverse matrix in this case would be V1 plus V2 for my first column, V1 minus V2 for my second column, 1/3 V3 for my third column, and 1/4 V4 for my fourth column. And there you go. That would be the inverse in this case. The problem in mission 3 is not this dumb. I wouldn't insult you by giving you this easy a problem. Like, you actually have to do some kind of algebra to like kind of unravel the equations. But you can solve that problem by like adding and subtracting the equations which I give you, something like that. All right, so the solution to the homework problem requires more creativity than this, but this hopefully gets you started. Yeah.
Is there an alternative way to do this involves setting up I equals?
No, I don't. Well, how would you do that? I shouldn't say no. I mean, what would you do?
So if you did like a substitution for E1, 2, 3, 4 with what we're given, then did I equals, and then like just the way you have it now, and then factor out the A, then inverse over the A.
I mean,
And then A inverse I would be A inverse, and you still have that, I guess.
you could. I suppose you could do something like, if the formulas are more complicated, right? You could do something like W1 is a linear combination of V1 through V4. W2 is a linear combination of them, right? This would lead to, I think, four parameters for each vector, which then would give you 16 equations and 16 unknowns if you take that approach. But that might not be an unreasonable approach if you're stuck, if you can't see through the algebra. If you did take that approach, I would be completely fine with you using like technology to solve that 16 by 16. Although I think the problem in the homework is not 4 by 4. I think, well, I don't remember. Anyway, let's go on. Okay, so here's something I get stuck on, like proof-wise. So we'll see if I can do it today. If I can't, well then, I guess I'll just leave it for your test. Okay, I'm joking, mostly. And so here's the theorem. A transpose inverse, watch it, is equal to A inverse transpose, supposing that the matrix is invertible. All right, let's see why this is true. So if A inverse exists, then that gives us what? That gives us A times A inverse is equal to the identity, and that's also equal to A inverse times A, right? So how would you get information about the transpose? An inverse of the transpose. How about we just take this equation which we're given and transpose it, right? Take the transpose of this equation. If we do that, that will give us what? A inverse transpose. A transpose is equal to I transpose is equal to A transpose, A inverse transpose. I may not need both of them, I'm just writing them both down. Why did the order of the letters swap? Remember, we used the sock shoes identity. Okay? And so this right here would reveal to us A inverse transpose times A transpose is equal to I, right? So that means that this is a matrix B such that B times A transpose is equal to I, which tells me then that A transpose inverse is equal to A inverse transpose. Oh, hey, today's one of the days I can prove it. Yay. I've gotten myself very confused about proving this identity at one point in my life. Maybe this summer, I don't know. Wait a minute, summer? Winter break, it's not a good sign. All right, so let's see here. So there's that. Example 5, you know, it could be something like this. Given well, forget the given. Let's just solve A B transpose equals to like 3i for B given A inverse exists. How would you solve that equation? Here's how I'd do it. So my first move would be to get rid of that pesky transpose. So if I take the transpose of the equation, I get, oh man, I think this problem is going to be too boring. I should have looked at my notes. So AB transpose transpose is what? Take the transpose of both sides. The transpose of the transpose is the thing again, right? It goes nowhere. So you got yourself a AB is equal to 3i, because the transpose of the identity is the identity again. How do I solve for B?
Multiplied by A inverse.
Yeah, just multiply by A inverse on what side, right? On the left, right? So that gives me A inverse AB is equal to A inverse times 3i, which simplifies to give me B is equal to 3 times A inverse. There you go. The solution to this is B is equal to 3A inverse. All right. Again, there is a much more interesting version of this in your homework, which of course you can ask me about in office hours if you get stuck or something. Let me talk then about a special kind of matrix, which is called an orthogonal matrix. Let's talk a little bit about that today. All right, so one of the things we should talk more about in here eventually, and I'll start the conversation now, is that the dot product from like calculus 3, right, which was what, like, you know, vector v dot vector w was v1 w1 plus v2 w2 plus v3 w3, right? If we're in 3 dimensions, this is the dot product. So if we think of vectors as column vectors, how can we write this in terms of matrix multiplication? This is the same as what? We can take v1, v2, v3, the row vector, right, times w1, w2, w3, the column vector. See, this is a 1 by 3. This is a 3 by 1. The answer is 1 by 1, right? We talked about this a little bit before, right? But this is a dot product. Now, of course, interestingly, this gives us what? This gives us actually the length of v, the length of w, times the cosine of theta, where if we were to picture it, v goes this way, w goes that way, right? Theta is the angle in between. And here, of course, the length of v is the square root of v dot v, and the length of w is equal to the square root of w dot w. So in like physics or Calc 3, we tend to just write the letter without the vector for the magnitude, right? That's the typical physics or science notation for length of a vector. Okay, so anyway, this is the dot product, and that's how it puts you in contact with the geometry in 3 dimensions. So an interesting question to ask is, what kind of matrix would it be? So here's the question, right? If, you know, if we take the vector v, right, and we map it to another matrix A times v, right, what property of that matrix would we get if it preserves the dot product? If this preserves dot product, in the sense that we have, let's say, AV dot AW is equal to V dot W. If we have that the dot product of the matrix times V with the matrix times W is equal to V dot W, right, for all vectors V and W, that seems like an interesting kind of matrix. Let's see what kind of matrix that is. All right, so let's use the things we know. We just learned, I just told you, that the dot product can be written as the transpose of the vector times the other vector, right? So as a matrix equation, this is exactly AV, and I really want to drop the vector, but I started, so I'll stick with the vectors. We don't try to put vectors in here too much, but I'll bear it for now. And over here, you got V transpose W. All right. But how does the transpose work? That's what? That's V transpose A W equals to V transpose W. So apparently, we have this equation for all V and W as to be a condition for such a matrix. So we get this for all choices of V and W. If you want to understand, you know, what this actually says about the matrix A, what we can do to make this equation sort of pop, if you will, is to choose the easiest possible choices of V and W to understand the nature of A. And so the easiest possible choices are the standard basis, right? Like E1, E2, E3. So like, if I put, let me just use EI transpose A transpose A, right, times EJ, that's equal to EI transpose times EJ. But what is EI transpose times EJ? That's the dot product of the ith and the jth standard basis element, right? So that, remember guys, is the Kronecker delta ij, right? On the other hand, what is this? If you allow me this small Menga style calculation, that is A transpose A, the ijth component of it. Because if we multiply on the left by the column vector, right, by the row vector with the 1 in the ith spot, if we multiply on the right by a column vector with a 1 in the jth spot, that picks out the ijth component, right? So we've got the ijth component of A transpose A is equal to this. But what this is the ijth component of what? The identity matrix, right? So this holds for all I and j. Therefore, we get the condition that the matrix must satisfy A transpose A equals to I. A transpose A equals to I. And this defines definition O n R is equal to A in Rn by n such that A transpose A equals to I. These are the set of orthogonal matrices. It's a set of orthogonal matrices. Now, if we studied these more deeply, now I started in 3 dimensions, but the truth is the derivation I just went through equally well works in 4 or 5 or 2 or however many dimensions you like, right? So these are the orthogonal matrices, and we'll learn as we go on a little bit later that there's 2 kinds of matrices in the orthogonal matrices. There are rotations and there are reflections, right? But all of them preserve the dot product, right? Which means, among other things, if you think about it, if you're preserving the dot product, since the dot product tells you the length of vectors and also the angle between vectors, that means that these kind of matrices, the transformations that correspond to them, preserve the angle between vectors that they transform and also the length of vectors which they transform. So orthogonal matrices are important. They define sort of the most natural coordinate transformations that you'd be interested in science and engineering. But listen, from the perspective of today and where we are in matrix theory, what does an orthogonal matrix have as its inverse? What's the inverse of an orthogonal matrix? The transpose, that's right. For an orthogonal matrix, the inverse is just the transpose. I showed you one of these the other day when we did that 2 by 2 matrix with cosine, sine, minus sine, and cosine. That was a 2 by 2 orthogonal matrix. And if you go back and look at that, you can see that the transpose was the inverse. Another thing you might go back and look at to appreciate is that we calculated like AA transpose and WW transpose, right? And W transpose W and A, we calculated the product of matrix and the transpose. What do you know in view of your homework problem now? This is kind of a fun thing to look back at. So check this out. Trace of AA transpose should be equal to the trace of A transpose A, right? Because you guys have proved in the homework that the trace of AB is equal to the trace of BA. These are not uninteresting statements because this could be a 2 by 2, this could be a 3 by 3, or whatever, and yet the trace has to be the same. If you go back and look at those calculations we did, you'll see every one of them works out like that, right? You do need to understand that a 1 by 1 matrix, the trace of a 1 by 1 matrix is just the number, but if you have that in mind. Anyway, I think that's all I got for you guys today. There are, of course, many applications to inverse matrices, which we'll eventually look at, probably next time, a little bit. If you guys have questions, feel free to ask them.